Watch this car driving in a straight line. As it moves, we can translate its physical motion into a two-dimensional mathematical trail. This specific chart is a displacement time graph. The y-axis tracks how far the car has traveled from its starting point, and the x-axis records the passing time. If you know what to look for, the steepness of this line reveals the car's exact speed. To find that speed, we calculate the gradient. We pick two clear points on our line. Let's use 2 seconds and 4 seconds. That gives us a change in displacement of 6 meters over a time interval of 2 seconds. Dividing that 6-meter distance by our 2-second interval tells us the car is moving at exactly 3 meters per second. Anytime you see a straight angled line on a displacement time graph, it means the object is moving at a constant velocity. We can extract invisible physical properties just by reading the geometry. Before starting your calculations, always check the labels on your axes.
This chart's y-axis tracks velocity instead of displacement, changing how we read the data. On this graph, a perfectly flat line indicates a steady speed of 6 meters per second. We can find the car's displacement by calculating the total area underneath this line. For this shaded rectangular block, we simply look at the dimensions. The base is the time elapsed, and the height corresponds to the velocity. Multiplying these gives total displacement. Calculating a geometric area on your screen directly translates to the exact measurable distance traveled on the road. When the car brakes, the velocity drops. This downward slope indicates deceleration. The gradient of this line reveals the rate of change, how quickly the velocity drops, which is the acceleration. Even though velocity is changing, the area rule still applies. To find the displacement during this braking period, we calculate the area of this right triangle. Now it's your turn. Using the triangle area formula, calculate the total displacement from the moment it started braking. Pause the video and give it a try. Using these basic geometric shapes bypasses the need for complex kinematics equations when solving motion problems. Let's walk through the math. Our base is 4 seconds, and our height is 8 meters per second. 1/2 times 4 times 8 gives us 16 meters total. The most frequent calculation mistake here is forgetting to multiply by 1/2. Always double-check your formula. To consolidate this, let's look at both motion graphs side by side. For a displacement graph, the gradient reveals the velocity. For a velocity graph, you have two rules. The area under the line equals displacement, and the gradient reveals the acceleration. Memorize this split-screen layout. Knowing these three exact visual rules provides the framework needed to decode and solve almost any straight-line motion problem on your exams. Physics exams embed multiple variables into a single scenario. You must extract acceleration, displacement, and forces from a paragraph of text. Two visual rules allow you to analyze these graphs. The gradient represents acceleration, while the area under the line represents total displacement. You then link visual findings to two physical laws: Newton's second law, force equals mass times acceleration, and momentum, the product of mass and velocity. These four tools, two visual rules and two formulas, form the core logic required to work through multi-part dynamics questions. Look at this standard exam problem. It contains specific triggers for the car's motion, starting from rest, uniform acceleration, constant velocity, and deceleration. These descriptions determine your graph coordinates. Starts from rest places our first point at the origin. Accelerates uniformly for 4 seconds to 12 meters per second gives us our second coordinate, connected by a straight line. The car then maintains that velocity for 4 more seconds before it brakes and comes to a stop at 10 seconds. The text has now become a complete velocity time graph. To find the initial acceleration, we calculate the gradient. The change in velocity over time, 12 divided by 4, results in 3. Precision with units is critical here. While velocity is meters per second, acceleration must be expressed in meters per second squared. Translating these coordinates and units correctly is the foundational step. An error in this initial acceleration will lead to incorrect force and momentum values later. To find the total displacement, we calculate the total area under the graph line. You can simplify the calculation by dividing the area into 3 geometric shapes: a triangle, a rectangle, and a final triangle. Calculating the area for each, using half base times height for the triangles and base times height for the rectangle, gives us 24, 48, and 12.
This sums to a total displacement of 84 meters. Now, consider the force involved. If the car's mass is 1,250 kilograms, calculate the braking force applied during those final 2 seconds. You can pause here to calculate it yourself. First, determine the acceleration from the gradient. A drop from 12 meters per second to 0 over 2 seconds results in an acceleration of -6 meters per second squared. This example shows the standard F equals ma format. Applying our values, 1,250 kilograms multiplied by -6 gives a force of -7,500 newtons. The negative result indicates the braking force acts in direct opposition to the car's forward motion. A common error is treating mass and weight as interchangeable. Mass is the amount of matter in an object, measured in kilograms, while weight is the force exerted on that mass by a gravitational pull. To find the car's weight, multiply its mass by the gravitational acceleration, 10 meters per second squared. Our car has a weight of 12,500 newtons. Momentum also requires careful unit conversion. As shown in this textbook example, a mass given in grams must be divided by 1,000 to convert it to kilograms before you multiply by the velocity. All these calculations describe the same physical journey. The area tracks the car's position, the gradient determines the force applied by the engine or brakes, and the momentum changes as the velocity fluctuates. This reference map consolidates the workflow. Use the graph to find acceleration and displacement, then use those values in the force and momentum formulas. Mapping this data ensures each calculation follows logically from the visual evidence of the motion.